Come on, switch it. Make sure you write your name. If you find that your friend didn't write your name, his name or her name, just give 0. Okay? All right, everyone switch. Okay. Intro. What you got?
0.0254 times 0.348.
Is that equal to value of C?
Yes.
Oma, what was your answer?
Same as him.
What is that?
0.3048 times 0.0254 squared, and then you have the meter cubed over feet times inch squared. That's right. For the unit.
Okay. Can I write it down?
3048
0.3048
times 0
times
0.0254
254
squared.
square.
And then you want the unit?
No, you did. Is that the value of C? I asked this. C equal to what? Yeah. Who got that? Is it? How long who didn't get that? Who get something else? Just you? Okay, Matt, could you please come here? Yeah, come. Help me please. Okay. What do you guess, sir? What's your answer? Oh, you put 1 over that. How about that? Who get like what he got?
Which direction are you asking us to go? It doesn't
I asked C value equal to what? That's the question. How much is C value? Give the expression for the numerical value of C.
Right, but
Unit is not needed and C is over
are
there.
you telling us that you equal the equation 1? So they equal the equation 1?
Okay. Let me write this. The volume of liquid phase. It's time for the solution, okay? The volume of liquid phase in the pipe is calculated from that equation, V equal to pi V squared over 4 multiplied by L. In equation 1, V is volume in meter cube, D is the inner diameter of the pipe in meter, L is the pipe length in meter. So everything is meter. Got it? Everything is meter and it doesn't need C. The unit conversion is 12 inch equal to 1 foot, 1 feet, 0.3048 meter, 1 inch equal to that. Give the expression for the numerical value of C. Unit is not needed in the following equation. V equal to C multiplied by that thing. Equation 2. In equation 2, V is still in cubic meter. D is inner diameter of the pipe in inch. Okay, L is the pipe length in foot. Is it clear why I'm reading this? Yeah. Okay, all right. Who like to go with this? You like that too? Okay, what do I like? What should I like? Say anything?
What is it?
Let me explain it my way. Let me explain it my way. Okay. Value of V stay the same. You agree? It's in cubic meter. Okay. The user should put L. They should put L in the unit of meter, but they didn't. They put L in the unit of feet instead. They should put L in the unit of meter, right? But they did not put L in the unit meter. So constant C should automatically adjust the input. Let's say they put L equal to 1. It should automatically adjust that to meter. So that is 0.3 something, 048. And the D square, the user should put D in the unit of inch or in the unit of meter, so that the left hand side is meter. But he or she did not. He or she put in the unit of inch instead. So parameter C should automatically adjust that to the unit of meter. Okay. When they put, let's say they put 1 inch square. So 1 inch square is not right. We have to convert that to inch. So we multiply by 0.00254 square. Does it make sense to you? You get 9, not very much. So if you do it correct, if you get it like this, 0.0254 square multiplied by 0.3048, like without that part, get 10, okay? If you put something else, give 9. If your friend didn't put anything else in it at all, give 0, okay? Are you done with it? Okay, please turn it in. Everyone have it? Okay. Please count how many get 9, how many get 10, and tell me how many subjects. Okay, in the actual test, it's not going to be this easy, okay? In the actual test, it's not going to be this easy. At least, if you put 1 over that number, you get 0. If not negative value, okay? But in the quiz, of course, you get 9. In the actual test, try to get it done correctly. Okay? So this thing will depend on the location of value C, right? If I put the value C on another side, it will be different. Okay? Alright, let's do the next lecture. Compression 1. Okay, in the field we have compressor. We need a compressor to meet the cell gas pipeline. This is a diagram that we have every time we have the well. Sometimes for a high pressure gas well, we heat it. We have high pressure separator, and we may have in the process stabilizer, we have compressor, and we have separator over there, wellhead over here, and compressor behind that box. Right? In this case, it's an example of low pressure gas well. Wellhead pressure is just 200 psia. Gas pipeline is 1000 psia. We need to somehow go from 200 psia to 1000 psia. That is multiplied by 5, right? That 5 ratio, we call it compression ratio. Right? Compression ratio of 5 is a little bit too much. So the recommendation is to use two stages of compression. Okay, you get the idea of compression ratio. Heidi Talbot, what is compression ratio? That. So discharge pressure or required pressure that we have divided by the inlet pressure or the pressure that we have. Okay, let's say I have 2 ounces of pressure in the tank. Okay, and okay, let's say gas that go to vapor recovery unit is 4 ounces. Okay, and we need to go to 50 or maybe 45 psig. So we go from 4 ounces to 45 psig. Okay, next to ID. Christopher L. Stricker. Hi, Christopher L. How much is compression ratio in this case?
Hello there, Christian.
How much do you want? How do you calculate the compression ratio? It has to do with 2 numbers. Okay. The trick here is we use PSIA. Don't use PSIG, use PSIA. So convert this to PSIA and convert that to PSIA first. That number divided by that number will be compression ratio. Got it? Don't use PSIG. If you use PSIG, that's 0. It's wrong.
What number divided by what number?
So what happened is, what we actually have to do is 40. Sorry. The answer will be 45 plus approximately 14.7 divided by 4/16 multiplied by 14.7 plus 14.7. That will be compression ratio. What? You can use 14.65 for Texas. Because this is in ounce. You see, that's in ounce. So when I divided ounce to pound, I get, so that gives me 0.25. Okay, I did it wrong. PSIG. Okay, I did it wrong. Okay, add that, then it becomes PSIA. Good. So the answer is I did it wrong. Okay, and the correct version is this. If you do like me, you get 0. Okay, do this. All right, that's the compression ratio. And this compressor we have seen it on the OTC already. It looks similar to this. It has this radiator at the back to cool it down, and we have what is that? Separator, inlet scrubber, and we have the compressor itself. Okay. Now let's take a look at the theory of compression a little bit. Okay. Okay. Number one that I want to know is about isothermal compression. Isothermal means everything is done at constant temperature. Okay. Operation is slow. Heat transfer is used to maintain temperature. So normally we cannot have isothermal compression. Okay. Whenever we compress gas becomes hotter. Okay. This is just in the theory. Isothermal means PV equal to constant for the ideal gas case. Okay. So what you need to know is what is isothermal process or what is isothermal compression. Constant temperature. Next one is isentropic compression. Isentropic means constant what? Entropy. Entropy is S. And okay, next is Jonah Stark. Mr. Stark, where are you? Jonah Stark. Great. What is physical meaning of S?
I don't know.
What is the name for that? S. Entropy. Okay. After Mr. Stark, Curtis C. Stacy. Curtis, what is the physical meaning of S or entropy? Physical meaning. What does it mean? Who?
It's like a loss of energy.
Okay. Brandon H. Sprague. Brandon H. Sprague. Okay. What is physical meaning for S? Physical meaning. What does it mean? Energy spreading apart. What does it represent? When S is a lot, it means what?
Very disordered.
Very disordered. Okay. So I would say S is the parameter that represents the chaotic level or randomness level of the system. Okay. You may not even know the unit, or you may not even know anything, but at least try to know like physical meaning, okay, what it means. So this means the system doesn't have any increase in the chaotic level. It stays as ordered as before, okay. That is isentropic compression. PV to the power of K equal to constant, and K is Cp over Cv for ideal gas. Okay. Cp, specific heat capacity for air, is 0.24 BTU per pound per Fahrenheit. Okay. Next is Benjamin. It's Benjamin Shipley. Benjamin, what is Cp value in the unit of BTU per pound per Roentgen? It's the same. Very good. Okay. So next part about the theory, you see that K value is important. Okay. PV to the power of K is constant. Different type of gas have different specific heat ratio. Air, K value is 1.4. K value doesn't have units because it's Cp over Cp. Okay. Argon, monoatomic is just 1.66. Helium, monoatomic is 1.66. Hydrogen is have H2, right? So it's 1.41. Nitrogen is N2, so it's 1.40. Water, 1.33. So this is like typical value of the specific heat ratio. Okay, you will eventually need this. Specific heat ratio is required to do the calculation of horsepower of the compressor. And we need to know all this theory because the formula is derived from this kind of ideal condition. Okay, so first we review this theory. Okay, another process we call polytropic process. N is a polytropic exponent, PV to the power of N equal to constant. Thus we can call it polytropic. If N equal to 0, we consider it as isobaric. Isobaric is constant pressure. N equal to 1, isothermal, constant temperature. N equal to K, constant entropy. N equal to infinity, constant volume. Okay. And if N stays between 1 and K, it's somewhere between isothermal and adiabatic process. Colton T. Shaw, what is adiabatic process?
Well, something's saying the same, though.
What did you say?
Something's
Something stay the same in adiabatic? Does temperature stay the same in adiabatic process?
No, that's isothermal.
So what stay the same for adiabatic process?
Pressure.
Pressure?
No,
No,
isobaric.
that's isobaric.
Heat.
Heat. Okay. Adiabatic mean, thank you, who said that? Mr. Lee? No. What's your name, sir?
Sean.
Sean, okay. Adiabatic mean we insulate it. We put the insulator around it. No heat coming in or no heat going out. Okay? No heat transfer across the boundary. Q equal to 0. No heat from the environment coming in. No heat from the system to the environment. Okay? That's adiabatic process. Let's take a look at the compression theory for the reciprocating, and we relate that to the PV diagram. The reason that we worry about this is the actual work required to calculate the horsepower come from that diagram. Is it important now? Yes. At the end of the day, we want to know how many horsepower do we need for the compressor. Hey, in my field, I have to do this. How many compression stage? How many stage do I need? Okay, and what about the horsepower? What horsepower do I need? Okay, horsepower, it will come in a little bit, but first, it comes from the area under the graph of this. So let's study this a little bit more. So this is PV diagram for reciprocating compressor. Reciprocating compressor move in a reciprocating motion, in and out like that. At the point number 1 is that point, we start with gas inside, okay? And it's low pressure. So pressure is low, but we have a lot of volume, okay? That is stage 1. This means we suck all gas in already. Both valves are closed and we're ready to push, okay? We're ready to push. When we push, okay, we have some gas molecule over there. When we push, it becomes denser, okay? It becomes denser. So when we push, look at this. This valve closed, this valve closed, and we push. Pressure go up, okay? Pressure go up, volume go down. So we go from point 1 to point 2. Good? When we compress it, we move from point 1 to point 2. After we move to point 2, then we push furthermore. When we push furthermore, the purpose is to release gas. So we open this valve, this sharp valve is open, we push more, so gas coming out at a constant pressure from point 2 to point 3. So gas coming out at a constant pressure. Alright, then we stop at point 3. At point 3, we still have high pressure, but we don't have much volume inside. So the next step is to suck gas in. So suction valve open, and we suck gas in. So mass coming in. When we suck in, we suck the low pressure gas. We take the low pressure gas in. So pressure go down, but volume go up. Okay, we didn't suck all the way yet. Then we move more. Okay. Or actually, I think I did it wrong. We suck gas in from when we go from 4 to 1. From 3 to 4 is not sucking gas in. From 3 to 4 is just decrease of pressure, expansion. So from 3 to 4, no gas is sucking in yet because valve is closed. When we move the piston back, it allows this gas to expand and match the inlet pressure. We have to decrease the pressure first before we can suck anything in. Okay, if the pressure inside is high, it cannot suck low pressure gas in. Okay, so I'm sorry, when we go from 3 to 4, it's the expansion process. A little bit gas that left over there. Why do we need to have some gas left over there? Why do we have some gas left over there? If we have some gas left over there, more clearance over that, is less efficiency, so it needs more horsepower to do the same job. So that gap reduce the efficiency. Okay, that gap reduce the efficiency. Louis, Rodriguez, why do we need that gap, Louis? What is that gap for?
I don't know, so you don't heat the metal with metal, okay?
Correct answer, very good. Smart. So if we don't have that gap, it's gonna hit, right? The piston will hit this chamber, and when it hits, it will break. Okay, it will get fatigue. We don't want that to happen. So we don't want to have it hit, like what he said. Correct answer. Because of that, we have some gas left. When we have gas left, we have to expand that gas first before this valve can open. Okay? So this valve open based on the pressure. It doesn't have like electricity, anything. So when it have enough pressure, then it can open, it like suck air in out. Good? One of the previous year problem is to relate this with that. So you got to understand the relationship between this and that. All right. Efficiency, when we talk about that gap for receipt unit, okay, we call it volumetric efficiency, or E sub V, capital E sub V. Capital E sub V calculated based on the clearance fraction, CL, clearance fraction. Okay. R is a compression ratio, and CL is clearance. So if we don't have any gap, this thing is 0, then efficiency coefficient becomes 1, very efficient, volumetric wise, okay, very efficient. But we need to have some gap. If we have a gap, let's say we have high compression ratio, R is a lot. What happened to that? Efficiency go up or go down? Down, right? Down. So if your compression ratio is, let's say, 10 or something, to the power of 1 over k minus 1, so this number becomes big, efficiency go down. Good? So we don't want too much compression ratio because it's not efficient. The derivation is from here. Last year I covered it, but this year let's skip it and have grad student do it. Basically, after we do compare the gas volume pound per cycle over the stroke volume of cylinder, then we get the volumetric efficiency equation. Okay? That's how it divides. Your job is write that down. Okay, that's your job. CL is from 0 to 1. Okay, CL should be like 0.1, 0.01 value. Let's talk about the work required. Once we know that, we can calculate horsepower. Okay, we have several lines in PV diagram. Okay, these come from that website. Maximum theoretical work or horsepower required for compression calculated from adiabatic compression process. What's adiabatic compression process? No heat coming out. It's getting hot, and just that. Okay, that is maximum theoretical work required. Let's take a look at this line. I have adiabatic reversible S2 line, reversible isothermal, another line. Okay, isothermal has lower graph. Lower graph means less area under the curve. Less area under the curve means less horsepower. Okay, less horsepower to do the same job. Actual phenomena we have PV equal to the power of n equal to constant. If we cool it down, have interstage cooler, we have that line. If we don't have interstage cooler, we have another line. Interstage cooler give us less horsepower required. Okay. maybe I don't remember if it's last year or 2 years ago, midterm exam, I have the question on the compressor. Give student, okay, inlet pressure, outlet pressure, tell me the compression ratio, okay. Then, and number of stage. Then you put the interstage cooler. If in your design, if you don't put interstage cooler, there's no point to do multi-stage, okay. We need, if we have more than one stage, we need interstage cooler. If you decide to not put it in the exam, that's wrong, okay? You always need interstage cooler for multi-stage compressor, okay? And in the exam, when you raise your hand, should I put an interstage cooler here? No, that's part of the question, I don't tell you that. All right, we're almost there. We have to know a little bit more on the first law of thermodynamics, then we can derive the horsepower equation. First law of thermodynamics, delta U equal to Q minus W. You may have seen this in other form, maybe W equal to Q minus delta U or something. It depends on the sign, the sign over here, the sign convention. If we have delta U to represent the change in internal energy with time, increase is positive, okay, and we define over the closed system, no mass in, no mass out. Q added to the system is positive. Work done by the system is positive. So if we have heat added to the system, that's positive value, and that work done by the system, okay, that's positive value. If we have heat added equal to work that is done by the system, then delta U, the change in the internal energy equal to 0. Good? Is that good? It's too good to be true. It cannot be like that. Okay? Q, second law of thermodynamics, which we will reach soon. Okay? It is impossible to extract an amount of heat QH from hot reservoir and use it all to do work. Okay? Some amount of heat QC must be exhausted to a cold reservoir. No perfect heat engine. It is not possible that we take 10 joule or 1000 joule of heat and convert all that to work. Okay, that's violate the second law of thermodynamics. Okay, there will be some heat coming out. Alright, that's second law of thermodynamics. This thermodynamic law, it has to do with intensive property and extensive property. Intensive property is independent of the amount of material. Okay, that's intensive property. Like pressure, temperature. If I have more water, it doesn't mean that I have higher temperature, right? Okay, so that's intensive. Extensive property, depending on the amount, like volume or mass. And we have energy in general is intensive multiplied by delta of the extensive. For example, P delta V is work, Q is T delta S. And you see that S is capital S, not small s. What is the difference between capital S and small s? Doug? Capital S and small s. Capital S is going to be extensive, depend upon mass or volume. It's not specific. When the people use the word specific entropy, that's small s. Okay. Specific entropy, that's small s. Specific heat capacity, that small c hat p or something. If it is not specific, it depends on mass. For example, I can tell specific heat capacity. Specific. What is the unit of specific heat capacity? Douglas? What is the unit of specific heat capacity? Joule per something. Per Kelvin? Per mass, per kilogram. Okay. So if it's just heat capacity, it will be just Joule per kilogram. Okay? When it's have the word specific, that will be per mass or per some kind of material. Okay, that is the second law of thermodynamics. Then I think we are ready to derive the derivation. Okay, we will use this equation again. This equation is for conservation of energy, steady state case. Steady state means it doesn't change with time anymore. Okay, when we look at it day 1 and look at it on day 2, it looks the same. That's steady state. Steady state doesn't mean that it doesn't move. Okay. All right. Delta is defined as out minus in. In English unit, this is a law. You may see that there are some more terms over here. In addition to the first law. First law just have W, Q, and W, right? How come we have more terms over here? Is that something wrong? Elizabeth, read the Elizabeth. Why do you have more terms over there? We have 3 more terms compared to the first law. What's going on? Elizabeth.
Breaking it down into its components?
Okay. This is steady state. Okay. Previously on the first law, this is defined over the closed system. No mass in or out. This equation allows mass coming in and mass going out. Okay, that's why it's have steady state. And it's also breakdown, like you said, it's have internal energy, and it's not it can have the change in the elevation, it can have the change in the kinetic energy. There's a mass coming in and mass going out, right? Question. So it have other term, PV term too. Okay. This comes from thermodynamic class. Unit is spelled out over here. Okay, this is engineering unit. GC is just conversion factor. GC actually has unit. It's the power mass, power foot per power force second square. Here's a conversion between power force to power mass foot per second square. And we have PSI to power force per square foot. How many people get 9? 25 get 9, and how many people get 10? The rest? Okay. 25 people who get 9. If please do it correctly. In the actual test it will be 0. Okay. Alright, there's a video. So what you need is that number. Okay. The more accurate version is at the back. That is for you to write in your information sheet. Okay. Ideal isentropic horsepower is this equation. We assume no elevation change. Okay. Isentropic means reversible and adiabatic. If the process is reversible, this means and adiabatic, this means S is constant, so Q also constant for reversible adiabatic. Okay. Neglect adiabatic make Q equal to 0, right? Neglect lost work due to friction. You see there's no friction term. Neglect the kinetic energy change. We have final form of delta H equal to minus W. This equation tells me that if we do work, W typically is the work done by what? System, right? Work done by system. When I compress gas, is it work done by system or work done on system? On, right? On. Work done on the system. So work done on the system is negative value. Negative value multiplied by minus 1, that becomes positive value. So delta H is positive. So this means if we do work on the system will get hotter. Okay, we compress gas becomes hotter. With that knowledge, just that equation, we can use this graph. Okay. The formula over here we have capital H and small h. Capital H is total enthalpy. Small h is specific enthalpy. Okay? Specific enthalpy has a unit of BTU per pound mole. Delta H is just BTU. This is a Mollier diagram, same diagram that we use for JT effect. Okay? It's a plot between enthalpy H and entropy S. Okay? When we do the work on the system, we compress a gas, pressure go up, right? Pressure go up. Temperature also go up. Okay. Let's go through the example. Let's go through the example. This is to calculate theoretical horsepower consumed by compressing 1 mm CFD measured at 14.73 psia and 60 F. So this 1 million standard cubic foot standard condition defined at that temperature and pressure. We compress from 65 psi A and 80 F to 215 psi A. The question that I have is, what is the discharge temperature? How much is the temperature after we compress it? Assume the gas gravity of 0.6. Okay. In this diagram, we read this. Pressure is that line. Pressure go up as we go this way. That pressure go up. So we go from 65 psi. 65 is kind of that line. That's 65. And 80 Fahrenheit. 80 Fahrenheit is like that line. So we start from that point. Okay. We start from that point. Let's have the zoom in version. We start from that point, we compress it until it reaches 215 psia. 215 psia is kind of this line, 215. So when we compress it, entropy is constant. Entropy is constant. Braxton Rees, why entropy is constant in this example? Braxton Rees. Braxton, B-R-A-X-T-O-N. Braxton Rees, why do we have constant entropy in this example? What? Because I could ask theoretical horsepower. That's what it is. I'm getting tired, I'm sorry. So when we calculate theoretical horsepower, that theoretical horsepower means S stay constant. Okay? When we say theoretical value, theoretical horsepower is S constant. We just go up. Okay? We just go up because S has to stay constant. We go from one pressure temperature to that, and then we can read the temperature from that point. Okay? The temperature from that point will be about 200 F. So I get the temperature at this temperature to be 230. I think we still have 2 minutes left. Okay, we do the reading. H1 equal to 400 BTU per pound. H pound mole. H2 equal to 1,800 BTU per pound mole. Where does H1 and H2 come from? Vertical axis, okay. This axis gives me H1 and H2. The difference between those two, when we use it, it's used to calculate the theoretical horsepower. In this case, I get 60.5 horsepower. This equation is a little bit long, I'm going to cover here. Any question for the last 20 seconds? No? Aya room will be 102 at today from 1 p.m. to 4 p.m. Okay? When you have questions,